Good evening, everyone. Good evening. Good evening, Rahul. Good to see you here. Good evening, everybody. Can you all hear me? Good evening, Anusha. Okay. Good evening, Ashu. All right. So, as we had the last class, and in that last class, I asked you whether you people would like to have some more questions on Hardy-Weinberg equilibrium, and like it was everyone, it was an unanimous decision that everybody wants to have one more class on Hardy-Weinberg equilibrium questions. So here it is. So this class will be Hardy-Weinberg equilibrium part 2, where we will discuss some questions which are related to Hardy-Weinberg equilibrium. We are going to see some numericals as well as some statement based questions based on this same principle. And also, we will be talking about some of the questions which are they were one of a kind of a question. Okay. And so far, they have not been asked in CSIR exams, but definitely they have a potential of being asked in CSIR exam, and they are little twisted, or you can say little complicated. Okay, so I have taken some examples of questions like that, and we will try to solve them here so that you get a good idea about solving this kind of question on your own. So everybody, after the last class, did you people try? Did you solve on your own some Hardy-Weinberg equilibrium questions, or at least the questions that we solved in the class only? Did you all try to solve it on your own? How are you able to handle it? Easily, finding it difficult, what difficulty you are facing, you can ask me here. Good evening, Achal, Priyanka, Legend, Sunshine. Okay, that's great, Rahul and Anusha, that you people solved some more questions, and it's good to hear that you are able to solve it and all. Yes, so let's get started. Good evening, Saujanya. Right. So this question was asked in December 2016. Which of the following is not an assumption of Hardy-Weinberg model? Population meets at random with respect to the locus in question. Second option, selection is not acting on the locus in the question. Third option, one allele is dominant and the other is recessive at this locus. And fourth option, the population is effectively infinite in size. Yes, anyone would like to answer? This is very easy. In fact, this was a part B question. Quickly, can I have some answers from you guys? You have to choose the option which is not an assumption of Hardy-Weinberg model. Yes, only two people have answered so far. What about others? I'm very surprised to see that everybody has got the wrong answer. Hardy-Weinberg model, the very first assumption of Hardy-Weinberg model is that it is a infinitely large population. Yes, Surendra, Rahul, Achal, Ashu. Yes, now you people are correct. One allele is dominant, other is recessive at this locus. Now this is never an assumption of Hardy-Weinberg model. Okay, so although we say that usually that is how we consider that the frequency of the dominant allele is p, frequency of the recessive allele is q, but it's not like that. The alleles have to be dominant and recessive. Even the alleles which are in co-dominant relationship or which are in incomplete dominant relationship, they also, their frequency also we can calculate. Okay, and their frequency of their genotype will still be this, equal to 1. Okay, so basically in case of Hardy-Weinberg equilibrium, it just says that suppose a particular gene has two alleles, so p will be frequency of one allele, q will be frequency of another allele. Okay, whether it's dominant, whether it's recessive, nothing is mentioned like that. Okay, but yes, it is clearly mentioned that the population is infinitely large population, randomly meeting population, with no mutation, no natural selection, and no migration happening in it. Okay, so the five conditions or the five the five assumptions of Hardy-Weinberg equilibrium for sure includes that population is of large size, population is randomly mating, there is no mutation, no migration, and no natural selection. Do you all understand? So population mates at random means randomly mating population is an assumption of Hardy-Weinberg equilibrium. Selection is not acting. No natural selection is also an assumption. And population is effectively infinite in size is also an assumption. Okay. So infinite in size, why do we consider? Because when the population is infinite in size, then the effect of genetic drift will be minimum. Okay, genetic drift, which is one of the evolutionary force that can change the genetic structure in random, so the effect of that is more when the population is large. Okay, is it understood, everyone? All right, so the people who got it wrong, okay, still it is all right because we are practicing, but make sure that you don't do this kind of mistakes. Okay, so you have to make sure that this basic points about Hardy-Weinberg equilibrium is clear to you. Okay, next question from CSR November 2020. In a population that is in Hardy-Weinberg equilibrium, 40% of the plants are recessive homozygotes and produce white flowers. 40% white flowers. If the total number of individuals in the population is 14,000 plants, the number of homozygous dominant red flowered plants and heterozygous pink flowered plants will be. So here what is given to us? It is shown that the frequency of white flowers, which is homozygous recessive, is 40%. Okay, means q square, just a minute. So q square is given as 40%. Just give me a minute, guys. I'm facing some kind of problem here. Okay, so Q square we have as 40%, and therefore what will be Q? So Q will be square root of 0.4. Okay, so square root of 0.4 will be equal to 0.632. Okay, now once we have got Q, so we can calculate P. That is very easy. P will be equal to 1 minus Q. So 1 minus 0.632 will give us 0.368. Yes, Rahul, absolutely correct. Your answer is correct. So P's value we have got. Now what is asked, very straightforward question actually this is, that if the total number of individuals in the population is 14,000 plants, the number of homozygous dominant red flowered plants and pink flowered plants you have to calculate. So now you have got P and Q. So red flowers means it is homozygous dominant. So red flowers, just a minute. So red flowers will be equal to, yeah, hi everyone. So yes, I am having kind of a network issue. So actually not network issue, like there's some problem in my system, I guess. Anyways, I hope it will work better now. So P and Q's value we have already written. So P's value we have got as 0.6368, and Q's value we have got at 0.632. Okay, now once we have got that, so if the total number of individuals in the population is 14,000, so what will be the number of red flowers? So red flowers will be equal to p square, but p square is its frequency, okay, or the proportion. So when we multiply that with the total population, that is when we will get the total number of red flowers. Okay, so substitute the value of p here, and p square multiplied by 14,000 will give you the number of red flowers. For pink flowers, it will be 2pq because they are heterozygous. 2pq multiplied by 14,000. Okay. So when you solve it, you will see the number that you will get will be nearby this option. Okay, it might not be exactly same number, because as you can see there are decimal points, so it depends whether like you have taken till 3 or 4 or 2 decimal points you have taken. So number will vary. Otherwise, if you see the numbers that you will get, okay, it will be very close to this option 2 only. 1, 3 and 4, they are very different. Is it understood, everyone? So I hope all of you are also sitting with pen and paper and trying to solve the questions as we are doing it here. Okay, and this is a quick announcement for the Watson Junoon Scholarship, and the Junoon batch enrollment for Biotechnica is going on. And in case you are not preparing for CSR exam, but you are preparing for your MSc entrances, okay, like Common University Entrance Test or IIT JAM or GATB, now Biotechnica provides classes for that also. So if you know somebody, you can tell them as well that they can enroll for these classes, and along with that they will get all the other benefits like workshop, hands-on project, hands-on training, certification courses, and chat support. And definitely they are also getting the VIP pass for the Christmas Congress, which is going to be conducted by Biotechnica in 2023. Okay, any information, any queries, any question that you have, please ring the toll free number and you will get more information on this. All right, moving to next question. That is from December 2014. So, in a random sample of 400 individuals from a population with alleles of a trait in Hardy-Weinberg equilibrium, 36 individuals are homozygous for allele A. How many individuals in the sample are expected to carry at least one allele, capital A? So the total population is given here as 400, and 36 individuals are homozygous for allele small a. Okay, what does that mean? Q square is equal to 36 by 400. Okay, now how many individuals in the sample are expected to carry at least one allele A? Okay, so one way of solving, there are two ways. Okay, so let me first tell you one way. So one way of solving this question will be like, you know that Q square is this, right? 36 by 400. So from there you calculate Q, then you calculate P, and then who all will be expected to carry at least one capital A? Whoever is P square and whoever are heterozygotes also. Okay, so you find their combined proportion, multiply it with 400, and that will give you the number of individuals which are expected to carry at least one capital A. Okay, but that is a very long way. The easiest way, okay, see, it is clearly mentioned that 36 individuals are the ones which are having small a genotype. Okay, so if you remove homozygous recessives from the population, what are you left with? You are left with homozygous dominant plus heterozygotes, right? And in the question, it is asking you to calculate that number only. So this question is that easy. So how many individuals are supposed to are expected to have at least one capital A allele? So it's very simple. It will be 400 minus 36. So 364 individuals. No multiplication, no square root, no squaring, nothing of those complex mathematical functions are required. A very simple subtraction. So for that, what is important? That you understand the question. Okay, you don't try to solve the question like every question in the same way. Every question is different. Understand the question, understand and comprehend the information that is given in the question, and then think how you can solve it better. All right. Yes, everybody's answer is correct. Good. Okay, another question. This is also a CSIR, previous year CSIR question only. The frequency of MN blood types in a population of 6129 individuals is as follows. So the table is given to you: blood type, genotype, and number of individuals. The frequency of LN allele in this population is. So this is a simple question of allele frequency. Okay, so when you have to calculate allele frequency, what you have to do? Very simple formula: number of alleles of that particular type present divided by the total number of alleles present in the population. Okay, now there are 6129 individuals in the population. That will mean that twice of that, because every individual is heterozygous, so twice of that will be the number of total alleles. Okay, and what about the ln allele? So how many ln alleles are present? So here the heterozygotes, each heterozygote will have one ln allele. Okay, so in these individuals there will be the same number of ln alleles. The homozygous who are for N blood type, so their genotype is LN. That means each individual has two LN alleles, right? So if it is the total number of such individuals is 1303, so twice of that many LN alleles they will be having among them. Okay, so twice of that will be 2606, right? So 3039 plus 2606 will be the total number of LN alleles. Okay, and that will be divided by the total number of alleles in the population, which will be twice the population size. Okay, so this calculation you all can do. So frequency of ln will be how much? 3039 plus 2606 divided by 2 times of 6129. Yes, so this calculation, you do it, okay, because you need the practice to do this kind of calculations also. So do it and tell me what answer you people are getting. Yes, Ashu, absolutely correct. And all of you also should get this option one. Right. Okay, again, one more question from previous year CSIR papers. So, in a population that is in Hardy-Weinberg equilibrium, the frequency of recessive homozygote genotype of trait Q is 0.04. The percentage of individuals homozygous for the dominant allele is. Okay, so quickly, guys, tell me what is given to us. 0.04 is what? Quickly. Yes, more answers. What is this value? 0.04. Yes, that's correct. So 0.04 is q square. Very good. Okay, so even though it is written just like this q, so you should not just go by that. You read the sentence carefully. Good job, everyone. So q square is 0.04. Okay, so frequency of recessive homozygous genotype for trait q is 0.04. So q square is 0.04. That means q will be equal to 0.2. So if q is equal to 0.2, p becomes 0.8. The percentage of individuals homozygous for dominant allele. Okay, that means p square. So p square will be equal to 0.8 square, which will be equal to 0.64. Okay, but you are asked to answer in percentage, so this will be equal to 64%. Yes, all of you got the correct answer as well. Right, so I think now you people will had some kind of confidence, right, in solving the questions. Okay, but you are getting confidence in solving the questions, but that does not numerical question, that does not mean that you lose your confidence in answering the statement based questions. Okay, because it is equally likely that you will get a statement based question also. Okay, so both of these things you have to be very good at, the concept as well as how to apply it in solving the numericals. Okay, so all these questions, okay, usually these questions you can see it is so simple, but these questions are all asked in part C. So easy 4 marks, you can have it on your name. Okay, next question. Now this question, uh yeah. Okay, so Sajani, are you asking something? Yes, in that time, yeah, this question, now this question was asked in this year's CSR exam, okay, the last one that happened in June. So consider alleles capital A and small a in a population. The frequency of heterozygotes will be highest when frequency of capital A is more than frequency of small a, frequency of capital A is less than frequency of small a, frequency of capital A is equal to frequency of small a, frequency of capital A and small a affect the frequency of homozygotes and not heterozygotes. What will be the answer? Yes, absolutely correct. Rahul, Sunshine, Ashwarya, Achal, Anupam. Yes. So answer is option 3. Okay. So basically, when we try to plot the Hardy-Weinberg equilibrium, okay, the conditions of Hardy-Weinberg equilibrium. So this is how the graph looks like. Okay. Where so in the x-axis, okay, across the x-axis, what we have the p or q, the allele frequencies. Okay. And on the y-axis, what do we have? We have the genotype frequencies. Okay. So on the y-axis is genotype frequencies, on the x-axis is allele frequency. So when a graph is plotted between them, this is how the lines look. Okay. So this red line is for homozygous dominant. Okay. This blue line is for homozygous recessive, and the green line is for heterozygote. Okay. So what do we see? What is the highest value of heterozygote? Somewhere here. So at this value, what is the value of P and Q? So P and Q's value is here. Okay. They are crossing each other at this point where both are 0.5. Okay, so the frequency of heterozygote will be maximum when allele frequencies are equal to each other. Okay, very simple. You will remember this graph. So this is how the graph will look, because as the p is increasing, q will decrease. Okay, it will be less than 1 only, because p and p plus q will be 1. Okay, and as the p increases, q will decrease, right? So this is how the relationship will look. Okay, so answer will be option 3, that is frequency of capital A is equal to frequency of small a. That is the time where the frequency of heterozygotes will be highest. Okay, this question was also in the last ASR exam which happened. So a scientist is using the Hardy-Weinberg equation to assess if a population is in equilibrium or is evolving. She recorded the following characteristics for the population. The size of the population very large, individuals are randomly mating, individuals are under natural selection, new alleles are added to the population through migration and dispersal, mutation rates are high. Which one of the following option contains all incorrect characteristics of a population in Hardy-Weinberg equilibrium? Very good, and all of you are excellent. Yes, correct. Right. So what is the answer we are getting? So size of the population very large is a characteristic of Hardy-Weinberg equilibrium. Individuals are randomly mating is also Hardy-Weinberg equilibrium. Individuals under natural selection, no. Alleles are added because of migration, no. And mutation happening, no. Okay, so C, D, E are the three conditions which will not make the population under Hardy-Weinberg equilibrium. So which of the following options contain all incorrect characteristics of the population for Hardy-Weinberg equilibrium will be option 2, C, D, and E. Okay, next question. The number of heterozygotes in the population is 8 times the number of individuals with homozygous recessive trait. What is the frequency of the recessive allele in such a population? Yes, I want you all to try and solve it. Condition is given to you. Number of heterozygotes in the population is 8 times the number of individuals with homozygous recessive trait. Okay, Vaseem, we'll see. What about others? What do you think will be the answer? Come on, guys, solve it. It's okay if you're wrong, but you will learn something here. No. So far, whoever has answered, that is wrong. Okay, so let's first write down what is given in the question. Tell me that. Number of heterozygotes in the population is 8 times the number of individuals with homozygous recessive trait. So what is the equation given? Yeah, Gayatri, Rahul, Anupam, Anusha, yes, you guys are correct. So what is the equation given here? 2pq, okay, number of heterozygotes in the population is 8 times the number of individuals with homozygous recessive trait is equal to 8 times of q square. 2pq, that is the number of heterozygotes, is equal to 8 times the number of individuals with homozygous recessive trait. Absolutely correct, Achal. So 2pq is equal to 8q square. Okay. Now what do we have? So you can, q is there on both sides. So you can cancel 1q here, 1q here. Okay. So what we will get? 2p is equal to 8q. Now how to go ahead of it? So in a equation, so if we have to find out the frequency of recessive allele, means we have to calculate q. So if we have to calculate q, so better to get the equation in the form, only variable should be in the equation is q. Okay. So is there any way we can change this p into q? Yes, there is a way, that p is equal to 1 minus q. Okay, so instead of putting p, we can substitute it as 1 minus q. So 2 times of 1 minus q is equal to 8q. Okay, open the bracket. So 2 minus 2q is equal to 8q, right? Now, when you move this to the other side, so it will become plus. So 10q will be equal to 2. Q will be equal to 2 by 10. When you solve it, so it will be 0.2. Okay. Understood, everyone? So this relationship can be anything, 8 times, 10 times, half. So just this is the way you have to solve it. Okay. So first you write down the equation, whatever you have to calculate. Okay. Whether it is P or Q, write down the entire equation in that variable only. Okay. And then solve it. Thank you so much, Vaseem. I really hope that these classes, these sessions are helpful to you. Okay. How about going for the next question? In the European land snail, Sepia nemoralis, multiple alleles or at a single locus determine shell color. The allele for brown, CB, is dominant to allele for pink, CP, and to the allele for yellow, CY. The dominance hierarchy among these alleles is in one population, sorry, is in this. Okay, this is the dominance of allele. Sorry, it came, there was some editing mistake. So this is the hierarchy of dominance. Okay, that CB is dominant over CP and CY. CP is recessive with CB but dominant over CY, and CY is recessive to both CB and CP. Okay, now in one population sample of sepia, the following color phenotypes were recorded. Okay, what is recorded? That brown is 236, pink 231, yellow 33, total 500. Assuming that this population is in Hardy-Weinberg equilibrium, that is large, randomly mating, free from evolutionary processes, calculate the frequencies of CB, CP, and CY alleles. So as you can see here, we are talking about 3 different alleles. Okay, but you know that we can modify the Hardy-Weinberg equilibrium equation in form of three alleles as well. In fact, in the last session that we had in YouTube, I have showed you one such example, right? That was asked in the previous year CSIR exam regarding ABO blood group. So using the same concept, you have to solve it. And I put this question intentionally so that you get a practice of how to solve for multiple alleles. Yes, there is no option. You have to tell me what values of CB, CP, and CY you are getting. Okay, so let's have a look. So this is the hierarchy of the genotypes is mentioned, the dominance, hierarchy of dominance is mentioned, right? So can you people tell me who all or which all genotype will have this brown color? Mm, no, Suresh, that's not correct. What you have got? Okay, quickly, guys, tell me who all will have the brown phenotype. What all genotypes will have the brown phenotype? So brown is the most dominant allele, right? So whoever is homozygous dominant, CBCB, whoever is CBCP, okay, and whoever is CBCY, they all will be having the brown phenotype. That's correct, Gayatri. Who all will have pink? CPCP and CPCY. Whoever will have yellow, only CYCY. Okay, now suppose, because we have to use in the for in the equation, so let's say that CB's frequency is P, CP's frequency is Q, and CY's frequency is R. Okay, so what do we have here? This is R square. What is R square? R square will be 33 by 500. So if R square is equal to 33 by 500, which will give you the value of 0.06. Okay. Suresh, if you have got this, till here it is correct, but this is R square. This is not R, right? So what will be R? R will be square root of 0.06, which will be equal to 0.26. So value of R is 0.26. Do you understand, Suresh? So till here you did correct, but it is R square, not R, because this is the number of individuals showing the yellow phenotype. Now, if you remember in the last class when we talked about this multiple allele, so once you have solved one, next what we will do? Just take that allele and another allele. Okay, it can be anyone. Either you take CB or you take CP. But if you take CB, there will be more number of values there. So instead of that, we can take CP and CY together. Okay, so pink and yellow, right? So if you consider pink and yellow, right? So what will be the equation? It will be CP, CP, or frequency of CPCP, you can say, plus frequency of CPCY plus frequency of CYCY, okay, will be equal to how much? So CPCP and CPCY is 231. So this value is 231 divided by 500. What is the value of this CYCY? It is 30 by 500. So plus 30 by 500. Okay. Now in this side, so what you can write it here? CP is Q, right? So it will be Q square plus 2PQ. Sorry, 2QR. Q square plus 2QR plus R square will be how much? So when you solve it on this side, you will get the value as 0.528. Okay. So and on the right, on the other side, so what is this? This is Q plus R whole square is equal to 0.528. So what will be Q plus R? So square root of that. So Q plus R will be equal to 0.73. And when you substitute the value of R, R's value we know is 0.26. So substitute the value of R and Q's value you will get, which will be equal to 0.47. Okay, so Q will be equal to 0.47. Right? Now you have got P and Q's value. So you have got R and Q's value. So you can substitute it in the formula here, that P will be equal to 1 minus Q plus R. And that will give you the value of P as well, which will be equal to 0.27. Okay, so answer will be this. Is it followed, everyone? So are you able to, everyone, so whoever were there in the last session, are you able to apply that concept here? So first you solve for the allele which is absolutely recessive. Okay, that you can solve easily, you can get that value. Okay, then you take that allele and another allele and do the equation, right? And from there you will get the value of other allele, and when you have the value of two alleles out of three, you can calculate the third allele as well. Okay, moving on to next question. Human beings carrying the dominant allele capital T can taste a substance called as phenylthiocarbamide, which is PTC. In a population in which the frequency of this allele is 0.4, what is the probability that a particular taster is homozygous? So this question, if you see, you here not only you have to apply the Hardy-Weinberg equilibrium, okay, the concept of that, but you also have to apply the probabilities as in genetics. Okay, probabilities in genetics, like how you see it in Mendelian principle. Okay, so that concept also needs to be applied here. Okay, so let's have a look. So human beings carry dominant allele T. Okay, so what is the frequency of this allele? It is mentioned as 0.4. Means P is equal to 0.4. So if P is equal to 0.4, automatically Q becomes equal to 0.6. Okay. Now, who all will be taster in the population? So what will be the frequency of tasters? So it's a dominant allele, means whoever is homozygous dominant and whoever is heterozygous, they all will be tasters of PTC. So P square plus 2pq. They all will be tasters. Okay. So you have the value of p, you have the value of q. So in the population, what will be the frequency of this? So you can calculate easily, and it will come as, so you substitute the values here and solve it. It will come as 0.64. Okay. Now the question is not that. Question is not asking you what proportion of the population will be able to taste PTC. Okay. The question is what proportion of what is the probability that a particular taster is homozygous? Yes, absolutely correct, Achal. So we have to go ahead. This is not our we have not got the solution yet. Okay. So this is the frequency of tasters in the population. Okay. Out of this tasters, you have to calculate what is the proportion of homozygous tasters. Okay. So homozygous tasters means who are p square. Okay. Out of the proportion which is of the tasters. So 0.64. So how much will be p square? P square will be 0.16 divided by 0.64. So it will be 0.25. Do you understand? Everyone? If the question would have been what proportion of the population will be able to taste PTC, or who all will be tasters, then your answer here is correct. Okay, but that is not. The question is what proportion of tasters will be homozygous. So you have to go to this extra step where the proportion will be of homozygous dominant divided by the total proportion of tasters. Because here Rahul question is what is the probability that a particular taster is homozygous? Okay, so out of all the tasters, see, for example, in a population, what you have, okay, so some are tasters, some are non-tasters. Okay, so this is your whole population. In that whole population, you have two groups. Some are tasters, some are non-tasters. Okay, now in this tasters also you have two groups. Some are homozygous dominant, that is p square, and some are heterozygous. Okay, so you don't have to calculate heterozygous. You have to calculate what is the chance that a particular taster is homozygous. Do you understand? That is why we have to go to this step. Okay, next question. A trait determined by an X-linked dominant allele shows 100% penetrance and is expressed in 36% of the females in the population. Assuming that the population is in Hardy-Weinberg equilibrium, what proportion of males in this population will express this trait? So this is again X-linked. Okay. Now remember, I have already explained to you about the X-linked alleles condition, that X-linked alleles, if they are present in females, so they will work like any other homozygous autosomal genes. But when it is present in males, because males have only one X chromosome, so whatever allele is there, it will be expressed. Okay, so for the X-linked alleles frequency in males, okay, so the genotype frequency in males is same as the allele frequency in the of that particular allele in the population. Okay, because males are not going to have two alleles of that particular gene. They are going to have only one allele because they have only one X chromosome. So this question, it says that 36% of the females in the population express the X-linked dominant allele. Okay, so what is this 36%? So 36% or 0.36 is what? They are p square plus 2pq, because here we are talking about a dominant allele, right? So how much will be q square? Q square will be 100 minus 36. Yes, do you all agree? 64. or q square will be equal to, so not 100, write it like this, because we are writing q square, which is a proportion. So 1 minus 0.36, so it will be 0.64. Okay, so if q square is equal to 0.64, so what will be the value of q? So q's value will be equal to 0.8. Right? Now, assuming that the population is in Hardy-Weinberg equilibrium, what proportion of males in this population will express the trait? Okay, so trait will be expressed by the dominant allele, not by the recessive allele. So if q is equal to 0.8, so p will be equal to 0.2. Okay, and this is the causative allele, right? So what proportion of males in the population will express the trait? It will be same as the allelic frequency. So answer will be 0.2. Did you all understand? Is it clear, everyone? Okay, excellent. So we have last 3 minutes. Let's see. Quickly, we will try to solve one more question. Yeah. A phenotypically normal couple has had one normal child and a child with cystic fibrosis and autosomal recessive disease. The incidence of cystic fibrosis in the population from which this couple came is 1 by 500. If their normal child eventually marries a phenotypically normal person from the same population, what is the risk that the newlyweds will produce a child with cystic fibrosis? So what is given to here? Okay, so I'll try to draw the pedigree chart and it will be easier in that way. So a normal couple, okay, they have one normal child, okay, and they have a child with cystic fibrosis, okay. And if the normal child eventually marries a phenotypically normal person from the population, okay, what is the risk that they will produce a child with cystic fibrosis? Right? This is the question. So if this person is affected, means this person has two recessive alleles. So if both the parents are normal and they have a child with cystic fibrosis, means both of them are heterozygotes. Okay. Now for this child, okay, the child of the newlywed to be a homozygous recessive, both of its parents are normal, right? So for this child to be homozygous recessive, both the parents has to be heterozygote, right? Now, what is the probability for them to be heterozygote? So that is what we have to calculate first. What is the probability for them to be heterozygote? Okay. Now, for this individual here, both of his parents are heterozygote. Okay. So when you do a cross, this is how the progenies will separate in the next generation. So this part is phenotypically different. Okay. And it is separate. They are suffering from cystic fibrosis. The rest other portion, they are normal. Okay. Now, when you see the normal progeny, in that 2/3 of the progeny are heterozygous. Okay. So if you pick a normal progeny from a cross of two heterozygotes, what is the chance that the person will be heterozygous? 2 by 3. Do you all agree? 2 by 3 will be the chance of this individual to be heterozygous. Okay. Now, what about his wife is coming from the population and she is also normal. Okay, she is phenotypically normal, right? So what it will be? It will be 1 by 500. Okay, is for the incidence of cystic fibrosis in normal population. Okay, that means q square in the normal population is 1 by 500. This is q square, incidence of cystic fibrosis. Okay, so q square is this much. So from there we can calculate q. So q will be equal to 0.45. So if q is equal to 0.045, sorry, if q is equal to this, okay, then in that case, what will be p? P will be equal to 1 minus 0.045, which will be equal to 0.955, right? Now, what is the probability that she is a heterozygote? So probability of her to be heterozygote here, because she is coming from the population, will be equal to 2pq. The value of p and q's we have determined here. So it will be equal to 0.086. Okay. So probability of this partner to be heterozygote is 0.086. Okay. Now, for them to have a child who is homozygous recessive, chances 1 by 4. Okay. Now, here 3 independent events have to occur simultaneously for the child to be affected. So, probability of child to be affected, okay, will be equal to what? Probability that father is heterozygous multiplied with probability that mother is heterozygous and multiplied with probability that their mating will produce homozygous recessive. Okay. So father to be heterozygous is 2 by 3. Mother to be heterozygous is 0.086. And for them to produce homozygous recessive is 1 by 4. Okay. So when you substitute these values and do the calculation, you will get the answer as 0.1. Sorry, 0.014. Okay. So here, this is a question which applies multiple concepts. Okay, you have to have an idea about pedigree analysis. You have to have an idea about Hardy-Weinberg equilibrium. Okay, so population genetics plus the human genetics part, and then you will be able to solve it. So it's a unique type of question, and that's why I added here so that you get a practice and get an idea how to solve this kind of question. Okay. So that's all, everyone. We have already shooted our time by 4 minutes. Thank you, everyone, for staying, and see you all in another session. And for the time being, again, the advertisement for our Junoon batch. If you want, if you know somebody who is interested, please tell them for the enrollment. Okay. Thank you, everyone. Have a good evening. See you all in the next session, and keep practicing.